All right, let's dive right in. In this explainer, we're getting into some pretty advanced database design topics, but it's the kind of stuff that's absolutely crucial for building systems that, actually work and don't fall apart. We're going beyond simple tables to talk about the rules that truly protect your data's integrity. So, have you ever done this? I mean, we've all been there, right? Or at least we've had that nightmare. You make what seems like a super simple change, and bam! Suddenly you've got a bunch of records just floating around, completely useless, with no parent, no context. These are what we call orphaned records. And honestly, they're a huge red flag that your database isn't doing its job. Today, we're going to fix that. So, the key to stopping this mess before it even starts is a concept called minimum cardinality. It sounds fancy, but really it's just the rule that says if a relationship is optional or if it's mandatory. Does a department have to have employees? Does an employee have to belong to a department? Getting this right is like the bedrock of data integrity. Okay, so let's get into it. First big question. When a child record, say an employee, absolutely requires a parent record, like a department, how do we make sure that parent row is protected? How do we stop those orphans from ever being created? Well, the good news is your database isn't totally helpless. It's already trying to look out for you. By default, right out of the box, a standard foreign key is going to scream at you if you try to delete a department that still has employees in it. That's, referential integrity 101. But just having the database say, nope, can't do that, isn't always what you want. What if we need it to be smarter, to take some kind of automatic action? And this is where we get to take the driver's seat. Beyond that default no action setting, we've got 3 other really powerful options we can set up. We can tell the database to automatically cascade the changes, which is pretty dramatic. Or we can have it set the key to null if the relationship is optional. Or we can even have it reassign the child to some kind of default parent. This is where you really start to make the database work for you, not against you. Let's zoom in on the most powerful, and maybe the most dangerous option, cascade. Picture this. You delete a parent row, and that kicks off a chain reaction. It automatically deletes all the child rows that depend on it. Now, this is perfect for things like, say, line items on an order. You delete the order, you obviously want the items on it gone too, right? They're useless otherwise. But you have got to use this one with care, because once that chain reaction starts, there's no going back. It's an automated, irreversible delete. Okay, so we've pretty much got the parent side of things covered. But any sharp developer watching this is already thinking, okay, but what about the other way around? How do we enforce a rule that says a parent must have at least one child? And as it turns out, that is a much, much harder puzzle to solve. And here's why it's such a headache. It's a logic puzzle. Think about it. To create a new employee, you need to know which department they belong to, right? You need that department ID. So the department record has to exist first. But if your rule is that a department must have at least one employee, you can't check that rule when you create the department because no employees exist for it yet. It's a total chicken and egg situation. So the real question becomes, when can you possibly enforce this rule? This basically leaves us with 2 main places where we can handle this problem, either deep inside the database management system itself or out in the application code that talks to the database. If you enforce it inside the database, you get guaranteed data integrity at the lowest possible level, but man, it can get complicated. If you do it in the application, you get a lot more flexibility, but you're also running the risk of someone using another tool, bypassing your application logic, and messing up the data. So what's the right call? Well, if you put the logic in the database using something like a trigger, that rule is absolute. It's always enforced no matter what. It's definitely the safest bet for your data's purity. But if you put it in the application code, you can build much more elegant, user-friendly workflows. You could guide a user through a multi-step process. Okay, first create the department. Now let's add its first employee. It's this fundamental trade-off between hardcore data-centric rules and a more flexible user-centric experience. So far, we've really only been talking about simple parent-child relationships, what we call binary relationships. But what happens when things get more complicated? What if a single event, like a sale, needs to connect 3 or more different things all at the same time? To wrap our heads around this, let's just start with what we already know. A customer can have many orders. Simple one-to-many relationship. A salesperson can also be tied to many orders. Another simple one-to-many relationship. Easy enough to model separately. But what's the thing that actually connects the customer and the salesperson together? You guessed it, it's the order itself. The order record becomes what we call an intersection table. It's not just a record of the order, it's a record of the specific moment in time where that particular customer and that particular salesperson came together for a transaction. And just like that, you've created a three-way, or as we call it, a ternary relationship. And here's what that actually looks like under the hood. The order table is the hero here. It has its own primary key, the order number, sure, but the important part is that it also holds foreign keys that point to both the customer table and the salesperson table. This one structure elegantly links all three of those entities together for one single event. All right, we've covered relationship structures. For our last section, let's talk about how we can use the database to enforce even more specific, more nuanced business rules. How do we model the things that absolutely must happen, or, maybe just as important, the things that must not ever happen? A must-cover constraint? It sounds new, but it's really just a business-friendly name for that exact problem we were wrestling with earlier: how to enforce a required child. The rule that says every project must be covered by at least one employee? That's just a minimum cardinality of 1. So all those strategies we talked about, using triggers in the database or handling it in the application code, they all apply right here. The must-not constraints, on the other hand, are often way easier to handle. These are the rules that stop you from putting in nonsensical data combinations. For example, it makes no sense for an employee's status to be active if they also have a termination date filled in, right? We can build that logic directly into the table's definition using what's called a check constraint. It's basically a little gatekeeper that rejects any new data or any update that doesn't follow the rule. It's a fantastic way to make your data self-policing. So with just these two types of constraints, the must cover and the must not, you can actually build a huge amount of your core business logic right into the database itself. And that brings us to the biggest idea of this whole explainer. When you boil it all down, the key thing to take away from all this is really simple. A well-designed database shouldn't just be a passive bucket that holds your data. It should be an active guardian of that data, an automated defender that enforces your business rules and protects your data's integrity 24/7. And that really leaves you with one big question to think about for your own work. When you look at your systems, is your database actively enforcing these rules with things like constraints, triggers, and well-designed relationships? Or is it just kind of hoping for the best, relying on the application code to get everything right? The answer to that question can make all the difference between having reliable, trustworthy data and a total mess. And that's a wrap on this explainer. Hey, if you found this deep dive helpful, do me a favor and hit that like button, share it with someone who might need it, and subscribe for more. Thanks so much for watching.